Good morning, my dear friends. I hope you all are doing great. So today, my dear friends, we'll be talking about the reaction enthalpy. So let's have a look, which is represented by delta HR. That is our reaction enthalpy. What is this reaction enthalpy all about? Let us discuss about it. Let us suppose I have reactants. And these reactants are changing into products. So this is our chemical reaction where the reactants change into products. Okay. My dear friends, in this particular chemical reaction, there will be always the change in enthalpy. Okay. And that change in enthalpy is known as reaction enthalpy, my dear friends. So now in this chemical reaction which I am talking about, it's a chemical reaction. If this chemical reaction is, let us suppose, endothermic, then delta HR for this will be positive if it is an endothermic reaction. Endothermic reaction. So the reaction enthalpy is positive. Now my dear friends, if I take one more chemical reaction where reactant changes into the product, okay, and for this reaction delta H is negative, it means this reaction is exothermic. I have already discussed this, my dear friends. Here the energy is absorbed. Reactants are absorbing the energy because delta H value is positive and here delta H value is negative. That means reactants are releasing the energy and changing into the product. So now we have two types of reactions with us. Either we can have endothermic or exothermic. And here the reaction enthalpy is positive and here the reaction enthalpy is negative, my dear friends. So what is this reaction enthalpy all about? You might have understood. This is basically the change in enthalpy of a reaction. Okay. It can be positive or negative when reactants change into products, my dear friends. So I will write down the change in enthalpy of a reaction, okay, when reactants are converted into products. So my dear friends, when we convert reactants into products, there can happen, two things can happen. Okay, the first thing is that for this reaction you can have reaction enthalpy as positive or you can have the reaction enthalpy as negative. So it can be endothermic or it can be exothermic, my dear friends. So I hope you have understood the change in enthalpy of a reaction when reactants are converted into products, okay, is known as reaction enthalpy. And we know that it's represented by delta HR. And one more expression which I have taught you in the previous class was that delta HR, reaction enthalpy, is equal to enthalpy of products minus enthalpy of reactants. Here also we can talk about the positive value or negative value, my dear friends. If HP is greater than HR, if enthalpy of product is greater than enthalpy of reactant, so obviously, let me write down here. In first case, if HP is greater than HR, enthalpy of product is greater than enthalpy of reactant, then delta HR value will be positive. So we will have here delta HR as positive. So it's endothermic. Now second point, if enthalpy of product is less than enthalpy of reactant, that means HP is less than HR, then we have here delta HR as negative, that is exothermic, my dear friends. So this was about the reaction enthalpy, how we write it down. But when the reactions become complicated, like the reactions in which we have more than one reactant or more than one product, at that time what we do, I am going to teach you that after this. Please make note of this. Dear friends, if you have a reaction of this pattern, let us suppose methane in gaseous state is being oxidized. If you burn the methane or if you oxidize the methane, what happens? This carbon will burn from methane, carbon will burn and it will become carbon dioxide. And hydrogen will burn and will give me water. So this is my chemical reaction, my dear friends. So in order to balance this reaction, let's have a look. I will take this 2 times. Okay. And this one I will take, how many hydrogens are here? 4. 2 we have here, we will take it 2 times. So here we have 2 plus 2, 4 oxygen, and here also we have 4 oxygen. So my dear friends, this is the balancing reaction. Let us mention the state here. This is gaseous, this is liquid, this is gaseous, and this is also gaseous. Now if I want to write down the delta HR for this chemical reaction, these are my reactants and these are my products. My dear friends, I was using this expression like this: delta HR is equal to HP minus HR. If you have only one product or one reactant, then this expression is enough. But here we don't have only one reactant or one product. We have more than one reactant and more than one product. At that time, this simple expression will not do the work. So what we are going to do, have a look. So my dear friends, here I will write down reaction enthalpy is equal to sum of the enthalpies of products. For a simple reaction, I told you that enthalpy of product minus enthalpy of reactant. And here we don't have only one product, we have many products here. Okay? So I will write down sum of the enthalpies of products minus the same thing. Enthalpy of product minus enthalpy of reactant. Here I am taking sum of the enthalpies of product minus sum of the enthalpies of reactants. And this expression can be easily understood by this particular factor, my dear friends. I will use a symbol sigma. This is also called as summation. Okay. So what I am going to do here, try to understand. Sum of the enthalpies of product. The sum will be given by this. Okay, my dear friends. So what I am going to do, have a look. I will write down H products. So here I am taking sum of the enthalpies of products. Okay. Now in products, there is one important thing you should remember, my dear friends. Look at the products here. These are my products. Here I have 1 mole, here I have 2 moles. That means if you have just 1 mole of products, then no problem at all. But when you have different moles of products, like here you have 1 mole, 2 moles, for representing the moles, I am using a stoichiometric coefficient here, my dear friends. Let's call it that AI. AI will represent the number of moles of products. Remember that. Number of moles of products. Now this is now the sum of the enthalpies of products. Okay. Multiplied by their stoichiometric coefficients. Means the number of moles of products. Minus again the sum of the enthalpies of reactants, that is H reactants. And reactants also will have here 2 moles and here we have 1 mole. So moles of reactants will be represented by, let us suppose, Bi. So let us explain each term now. This is basically known as a symbol sigma, and this sigma represents summation. That is sum. Summation means sum total. Okay? That AI represents stoichiometric coefficient, is a stoichiometric coefficient. And what does it give? It gives number of moles of products. Number of moles of products. Okay. So now HP is nothing but it's the enthalpy of products, my dear friends. So this HP is the enthalpy of products. This sigma symbol will represent summation, that is sum. Okay. AI will represent the stoichiometric coefficient, that means number of moles of products, and HP will represent enthalpy of products. Same is the case here. This guy will represent the summation. It's a summation sum of, to represent sum total or total sum. Okay. BI represents, it's a stoichiometric coefficient. It will represent, it will give me the number of moles of reactants. It will give me number of moles of reactants, my dear friends. And this HR is nothing but it's the enthalpy of reactants. Enthalpy of reactants. So my dear friends, you might have understood now the expression for delta HR. So this is the expression for the delta HR. That is the sum of the molar enthalpy, the sum of the enthalpies of products, okay, multiplied by the stoichiometric coefficient minus the sum of the enthalpies of reactants multiplied by the stoichiometric coefficient of reactants. So this is our expression. Through this expression, we can calculate delta HR for this particular reaction. But before writing delta HR for this reaction, I can further convert this expression into the molar expression, my dear friends. I can take the molar enthalpy of products, sum of the molar enthalpy of products minus sum of the molar enthalpies of reactants. So I can convert this molar enthalpy of product into molar enthalpy of product, and also this thing also I can convert it into molar enthalpy of products. Please make note of this, and after this I will write down how to convert it. Dear friends, we have converted now. You can have a look here. We have taken the summation of the enthalpies of products, sum of the enthalpies of products multiplied by the stoichiometric coefficient minus sum of the enthalpies of reactants multiplied by the stoichiometric coefficient of reactants. That was my expression. Let me convert it into the molar form, molar enthalpies. So if I will write down here delta HR, that is reaction enthalpy, I will use the same expression here. AI, in place of HP, that is enthalpy of products, I will write down HM of products. This HM will represent molar enthalpy. Molar enthalpy. That is the only change I am doing, molar enthalpy of products. HMP will represent molar enthalpy of products. Okay. Now look here, for this expression I can do the same thing. Let's take the sum. Let's take on the stoichiometric coefficient of reactants, that means number of moles of reactants, and HR I will convert it into HMR. That will represent the molar enthalpies, or you can say enthalpy. Let me just change it here, molar enthalpies of reactants. So now let us take on our reaction and derive an expression for delta HR for this reaction, my dear friends. Okay. So what I am going to do, first thing you remember, I need to take the sum of the molar enthalpies of products. Okay. So these are my products. Correct, my dear friends? So let us take on the molar enthalpies of these products, my dear friends. So first of all, I will take carbon dioxide as my product. So have a look here. CO2 in gaseous state. Correct? And which enthalpy I have to take for the product? For products, I have to take molar enthalpy. Let me write down here. So this is the molar enthalpy of which product? Carbon dioxide. But there is not only one product, there is one more product also. But multiplied, molar enthalpy of product should be multiplied by stoichiometric coefficient. So this one is here, stoichiometric coefficient, my dear friends. That means it will represent number of moles. So how many moles we have here? Stoichiometric coefficient is 1. So I will write down here 1. So this 1 will represent, my dear friends, AI or AI. And HM is the molar enthalpy of products. This is my product. So I am writing molar enthalpy of carbon dioxide because carbon dioxide is my product. But do you think there is only one product? No. There is another product also. Who is that? Water. Water is another product. So I have to take the sum of these two because my formula is the sum of the molar enthalpies of products. That means I have to take the sum of these two. So let me take another one also which is also a product. So I will write down molar enthalpy of now water. So molar enthalpy of water which is liquid. Tell me, if I take molar enthalpy of water, so I am taking molar enthalpy of product and that product is water multiplied by AI. What is AI for water? 2. So AI is a stoichiometric coefficient, that is 2 here. So it will become expression like AI molar enthalpy of carbon dioxide plus AI molar enthalpy of water. But water is how many moles? 2 moles. So now this entire expression is your sum of the molar enthalpies of products. This entire expression, my dear friends. Because here products are carbon dioxide and water. So I have taken their sum. This symbol will represent the summation or sum total or total sum. Correct? Now, minus. I have to take on now sum of the molar enthalpies of here reactants. Sum of the molar enthalpies of reactants I have to take here, my dear friends. So let's take on, these are my reactants now, methane and oxygen. So I will take on now molar enthalpy of methane. Yes. So I took HMR, molar enthalpy of methane. Now I need the stoichiometric coefficient Vi. So here this is the stoichiometric coefficient for product and this 1 and this 2, they are the stoichiometric coefficients, means which represent number of moles. Stoichiometric coefficients, they give us number of moles. So if I am talking about methane first, molar enthalpy of methane multiplied by Bi. What is the Bi in case of methane? 1. So multiplied by 1. Let's take the sum. Sum will be basically here for another reactant we have oxygen. So I will take molar enthalpy of O2 which is in gaseous state. This guy is also in gaseous state. And how many moles of oxygen I have here? 2. So 2 will represent here Bi. So I will represent here 2. Now my dear friends, what I am going to do is have a look. So I have taken the sum of the molar enthalpies of products multiplied by their stoichiometric coefficients minus sum of the molar enthalpies of reactants multiplied by their stoichiometric coefficients. So this is for products and this is for reactants. And for this thing we have an expression that is summation of Bi, that is HMR. That is the sum of the molar enthalpies of reactants. Sum of the molar enthalpies of reactants. So sum of the molar enthalpies of products minus sum of the molar enthalpies of reactants will give me the delta HR. So now my dear friends, I hope you have understood. Let me remove this expression now, you have understood it. And let me remove this expression and you have understood. Let's revise it for just a minute. You have taken one chemical reaction and finally you have taken delta HR, reaction enthalpy. That is the sum of the molar enthalpies of products multiplied by their stoichiometric coefficients minus sum of the molar enthalpies of reactants multiplied by their stoichiometric coefficients. Correct or not? Now for this chemical reaction, these are my products. So I have taken the sum of the molar enthalpies of my products, the sum, minus the sum of the molar enthalpies of my reactants. So this minus this will give me the delta HR. I hope everybody has understood my point or not. And in this entire process, this HM stands for molar enthalpy of either reactants or products. Here it is HM for reactants, here is HM for products. Please make note of this. I hope you have understood. Dear friends, let's talk about now standard enthalpy of a reaction. Usually we were talking about enthalpy of a reaction, that was delta HR, and we have discussed it in detail about that particular thing. Now we are talking about standard. So new term has come, standard. That's very much important here. The enthalpy change of a reaction. Same thing is happening here. Reactants will change into products, my dear friends. Reactants will change into products. And now there will be either a release of energy or the gain of energy. It will be either endothermic or exothermic. Let us suppose this reaction can be either exothermic or this reaction can be endothermic. But this delta HR will give me enthalpy of a reaction. Which thing? Enthalpy of a reaction. But here I am talking about the enthalpy change of a reaction when all the participating substances are in their standard states is known as standard enthalpy of a reaction. So here I am not talking about enthalpy of a reaction. Here I am talking about the standard enthalpy of a reaction. And in standard enthalpy of reaction, the participating substances, those substances which participate in the chemical reaction. Who is participating in the chemical reaction? Reactants, obviously. The reactants, okay, they have to be in their standard states. So these reactants have to be there in their standard states. So the reactants are participating in the chemical reaction and the reactants should be in the standard states. Then reactants will change into the products and the energy will be either absorbed or released. If it is released, exothermic. If it is absorbed, endothermic. But it is not the reaction enthalpy, it's a standard. Because conditions are standard. So I will mention here not. Here also I will mention not. Now what is the meaning of this not? Let us explain it. Have a look, my dear friends. Delta HR is the reaction enthalpy. When I put not here, this not is basically here now superscript, because something which is written up becomes superscript. And this superscript is pronounced as not. And this not will represent standard condition. Represents standard condition. So now delta HR naught is basically the standard enthalpy, this one, the standard enthalpy of a reaction, my dear friends. Now you will be still thinking, how come we get to know that the reactants are in their standard states, correct? So you have to remember these particular conditions. Usually in the NCERT book, they will find out the standard states of the reactants or the substances like solids, liquids and gases. Because reactant can be solid, liquid or gas. So they usually compile the values. If you find out in your NCERT, they will compile the values at 25 degrees Celsius or 298 Kelvin. But it's not necessary, my dear friends. Sometimes the standard state of some substance can be at higher temperature or lower temperature also. But the values given in the NCERT will be at 298 Kelvin. Please remember that. It can be more than 298 or it can be less also, but in NCERT it's at 298, so we'll mention 298 right out here. Second thing, all gases at 1 bar pressure. If you take gas as a reactant, and that gas should be at 1 bar pressure. And even you can mention in place of 1 bar pressure as 1 atmosphere pressure also, because there is not much difference. Okay. And if you take liquids and gases, they have to be in the pure state. They have to be in the pure state. I am talking about the standard states of reactants. Reactant can be solid, reactant can be liquid, reactant can be gas. So when I talk of standard state, the temperature is 25 degrees Celsius and the gases have to be at 1 bar pressure. If you have liquids and the gases, they should be pure. Pure in the sense means, I mean to say that they should be in their pure form. Okay? And finally, all solutions are at 1 molar concentration. If you take a solution, okay, then the solution has to be at 1 molar concentration. These are the standard states. So the participating substances, okay, have to be there in their standard states. Means they have to be at 298 Kelvin temperature. Okay, they have to be at 1 bar pressure. Yes, they should be in the pure form. Yes, if it is a solution, then it should be of 1 molar concentration. Then only we can calculate delta HR naught. I hope, my dear friends, you have understood this particular thing. And same applies for the solid also. Solid should be also in its pure form. Yes, at 298 Kelvin temperature. Even for solids also that applies. I hope, my dear friends, you have understood the meaning of this delta HR naught. Now if the expression we will write down for delta HR naught, it will be like this. Delta HR naught, that is the standard enthalpy of a reaction, will be equal to HP naught, that is the standard enthalpy of products, minus standard enthalpy of reactants. So this is the standard symbol right out here. You can mention also like this, delta HR naught is equal to sum of the standard enthalpies of products multiplied by stoichiometric coefficient minus the sum of the standard enthalpies of reactants multiplied by the stoichiometric coefficient. This way also you can express it. Or even you can express it in terms of molar enthalpies as well. Have a look here. So AI, then you can use HMP naught minus, so BI HM R naught. So my dear friends, you can express the standard enthalpy of reaction in this way as well. Friends, I hope you might have understood now today enthalpy of reaction and standard enthalpy of reaction. Enthalpy of reaction can be taken at any temperature and pressure, but the standard enthalpy of reaction can be taken under standard conditions. Yes, and the participating substances, I told you, should be in their standard states, in their pure form they should be. And usually the temperature taken is 298 Kelvin. Yes, but it is not the fixed temperature. Whatever the values we are taking in NCERT, they are mainly at 298 Kelvin temperature. So I hope you have understood all this. And delta HR is your enthalpy of reaction, and delta HR naught will represent the standard state, standard enthalpy of reaction. I hope you understood, my dear friends. Take care of yourself. Yo.